Alright, welcome. In this video I want to pose a exercise that I presented in an earlier video. And this is related to a heap and possibly a recursive implementation of a heap, which is not the standard way to do it, but if we were to do it this way we might pose ourselves a unique problem. And so I'm going to start out by posing this problem by just showing the place values or the place locations that you would add an element into a heap. Already made a mistake here. These are position 1, 2, 3, 4, 5, 6, 7. Maybe I'll just continue a little bit here. 8, 9, 10. Okay, maybe I'll stop here. And I'll say that if I want to get to position n equals 10 in my heap, we can see here that the path I need to take is to go left, right, left. So the path to position 10 is left, right, left. Now this poses an interesting problem because actually we now want, if we were going to add an element here, we would be adding an element to this location here, position 11. And if we were doing this recursively, then we would want to be able to go down to position 11 without having to traverse the whole tree and visit all the nodes and find position 11. We'd want to know what path brings us to position 11. We would want to be able to calculate it ahead of time and just know, like we did for position 10, position 11 is going to be left, right, right. So maybe we can see here 11 would be left, right, right. And so in general, I want to know what the pattern is for n. If I give you an n, I want to know the sequence of left, rights, and lefts that are going to take me down to position n, like we've just solved for these two simple problems here. So I want to pose this as an exercise. I am going to solve this exercise for you. But if you want to have a little bit of time working on the exercise yourself, maybe pause the video and take out your pencil and paper and see if you can figure it out yourself. So I'm going to pose a couple key questions that you can answer for yourself. The first one is, I want to know what the path is for n equals 42. What is the sequence of lefts and rights? And there's more than one way you could figure this out. So go ahead and take a moment and do that. And if you get it, if you think you figured it out, well, you maybe have either put in a lot of work to figure it out, or you've maybe been clever and figured it out. If you're clever, then you should be able to give me the sequence of paths for this larger number, 1337, as well, using the same technique. So again, at this moment, if you want to do it yourself, pause the video and go ahead and try it yourself. If not, I'm going to give you a couple hints now. So if you try a little bit and you need a hint, here's a little bit hint of how to go. So what I did to start out, one way to start out is we could keep drawing this and go further and further. And I think in a previous video I said we know our next row is going to have a 16. The next one's going to be a 32. The next one's going to be a 64. So if I really wanted to here, I could be, okay, 32, 33, 34, write them all out, 42, and see if I could figure out what that sequence is. Now I don't really want to do that, build the whole tree, because I know that even if I did solve the tree that way, it's not going to help me get this one. I don't want to draw out 1,000 nodes and figure out that path. So what I'm going to do instead is I'm going to take this, what I've got drawn so far, and I'm going to create myself a little bit of a table here. I'm going to maybe put n here, sort of like I've got over here. I'm going to put my path here. And let's start with n equals 1. My path here is, and I'm going to be careful, I'm just going to put a dash and say there's no path here, already there. 1 is the root. Okay, so what's the next value? Well, 2 then, we can see here, 2 is left. And 3 then is right. Okay, now my goal is to do this in hopes that maybe I'll see a pattern. Let's continue. 4 looks like it's going to be left, left. 5 left, right, left, right. Now we're going right, left, and right, right. So 6, right, left, and 7, right, right. Okay. Now, often after writing a few of them, you start seeing a pattern, and some of us might already see a pattern. And if you do, great. Run with it. Pause the video, see if you can figure it out. If not, follow with me. I'm going to do a few more. We got to 7. Let's do 8, 9, 10. 8 looks like that one is left, left, left. 9 looks like it's left, left, right. 10 we had already figured was left, right, left. And 11 we also saw was left, right, right. Okay. So again, if you've already seen it, if you've already figured out a pattern, you might see a way to go with this. If not, again, I want you to maybe think a little bit about this, practice, maybe write down a few more levels. The last node on this level is 15, so we might want to keep that in mind as we go down here. But for me, what I find is it's kind of hard to see the pattern. Some of us might already see it if you've got a good instinct. Unless we start writing this value n in a different way. So here I'm going to write n, but I'm going to write it in binary instead. So again, 1 written in binary is just 1. So that's pretty easy. 2 written in binary is 1, 0. 3 written in binary, 1, 1. Okay. You might be seeing a pattern yet. If not, let's keep going. 4 is 1, 0, 0. 5 is 1, 0, 1. 6 is 1, 1, 0. And 7 is 1, 1, 1. Okay. Again, maybe you're seeing a pattern. If not, let's continue. 8 is 1, 0, 0, 0. 9 is 1, 0, 0, 1. 10 is 1, 0, 1, 0. And 11 is 1, 0, 1, 1. Okay, hopefully this is enough for us to see a pattern here. What do we know about binary numbers? One thing we know about binary numbers is every binary number, except for 0, starts with a 1. What that means is that bit, it's a good placeholder, it's important as a placeholder, but it doesn't tell us very much about the number. So I'm going to actually go ahead and delete that number out. So I've gone and I've converted my number to my position to binary, and I've deleted out that first one because the first one is there for every number. And now what I'm going to do is I'm going to read my numbers out where my 0 must be a left and my 1 must be a right. So if I do that, I can see here, let's say like our 8 had 0, 0, 0 was a left, left, left. That's exactly what we've got here. So if we want to go and solve our problem then, we need to know what 42 is in binary. And let's maybe do that together. 42 in binary is going to have 1, 30, 32. Okay, that leaves us with 10. So that's 0 16s, 1 8, no 4s, 1 2, and no 1s. Now remember, we're going to delete out that first 1. It doesn't do anything for us. And we're going to capture the rest of them here. And we're going to follow our pattern. So this must be left, right, left, right, left. So the sequence of lefts and rights I need to get to, or I need to follow to get to position 42, is left, right, left, right, left. Okay, we figured it out without having to draw out the whole tree, which is great, because now that means if someone asks us this question, this is a great interview type question, what position is this? What sequence of left and rights do we need to follow to get here? Well, again, we can do that with by converting this number to binary. So let's do that. This one's a little bit harder if you know your powers of 2. It looks like it's going to be a 1024 So let's do this sort of following our algorithm. So we'll take our value, we'll subtract off. So 3, it looks like we end up with 313. So here I'm writing my number down. This is 1, but this is in my 2 to the 10 spot. Do we have a 512? It looks like no. Do we have a 256? Yes. So let's 256. All right, so 13 minus 6 is 7. 11 minus 6 is 5. We have 57 left over. Okay, so 57 left over. It looks like we don't get a 128. We don't get a 64, but it looks like we get a 32. So we'll subtract out here. 5, 25. So where were we? We're at 32. Do we get a 16? Looks like we do. That gives us 9. And that gives us an 8 and a 1. So again, deleting out the first one and reading them off here. Looks like we have a left, right, left, left, right, 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 left, left, right. That should be the path to arrive at position 1337. Okay, so one of the reasons why I've posed this little exercise is it helps us think as a computer scientist. And one thing we need to remember that as computer scientists, we need to get very familiar with base 2. So we want to practice working with base 2 and maybe memorize our powers of 2 up to a good number, up to 2 to the 10. You should definitely know all of those. Up to maybe 2 to the 16 is a pretty good range as well. And so practice with those, and then again, this is a great sort of interview exam question where someone might ask you, what is the sequence of lefts and rights to reach position, you know, n in a binary tree or a binary heap as we've been thinking of it here. And so it is worth knowing and practicing for that reason as well. Now, if you were to implement a heap in this way, you would have the problem of trying to isolate these bits and using them to move left or right. That's something you could do, but I think I mentioned in a previous video that more often than not we implement a heap using an array instead of a linked structure, so we wouldn't actually have to face this recursive problem on the way down. We have a much easier way to find the location. It's just the next location in our array. All right, this is all that I wanted to cover on the topic of minimum heaps or binary heaps. In these quick series of videos. In the next series of videos, or in the next video, I want to take a look at some data compression techniques. In particular, we're going to take a look at Huffman compression or compression using Huffman trees, and also LZW compression technique. So please stay tuned, and thanks for watching, and we'll see you in the next video.